Welcome everyone. Today we're going to go over Chapter 6, Section 3, Logarithms and Logarithmic Functions. Well, you'll learn today how to define and evaluate logarithms, use inverse properties, which we've gone over before, inverse properties of logarithmic and exponential functions, and then we'll graph logarithmic functions. So, well, what the heck is a logarithm? Well, you know that 2 to the second equals 4, and 2 to the third is 8. Pretty obvious, right? However, for what value of x does 2 to the x equal 6? Well, we know that it has to be somewhere between 2 and 3, right? Because 2 squared was 4, 2 to the third was 8. Okay, 6 is between 4 and 8, so it's 2 to the 2 point, it's going to be some kind of decimal, all right? So there actually is a way to calculate it, and that is using what are called logarithms, all right? So mathematicians define this x value using a logarithm and write x equals, and then this expression right here, which if we just go down the bottom, it actually tells us how to pronounce it. So it's pronounced log base 2 of 6. Log base 2 of 6. All right. So if we go down to the bottom here again, the definition of logarithm with base b, let b and y be positive real numbers with b not equal to 1. All right. The logarithm of, because by the way, if it was just 1, it would just be 1 to the whatever power. So you would still end up with 1. So that's why it says not equal to 1. The logarithm of y with base b is denoted by log base b of y is defined as, and then you guys are going to see this a lot. Okay. Log base b of y equals x, if and only if b to the x equals y. So basically what we're going to do is we're going to practice rewriting expressions one way and then the other way. All right, one way and then the other way. Just basically an important thing to keep in mind, okay, is when you're writing it in log form, this x, basically just keep it in mind as the exponent, okay, the exponent of, right, in that case, that x. All right, so keep that in mind when we go to the next page. Okay, so got a little reminder at the top about how we can transform one to the other. Okay, so I want everyone to keep in mind, okay, that this x is just the exponent of the original. All right, so basically, if you think about it, when we rewrite all 4 of these, that's going to be an exponent, that's going to be an exponent, that's going to be an exponent, that's going to be an exponent. Okay, the b up here is going to be the base, and the y is going to be what it's equal to. So 2 to the 4th equals 16. That's how you would rewrite that. And does that work? Yeah. 2 times 2 times 2 times 2 is 16. Okay. 4 to the, again, remember this guy's the exponent, equals 1. Does that make sense? Yes. 4 to the 0, anything to the 0 power is 1. Check. 12 to the 1st equals 12. Does that make sense? Yeah. Anything to the 1st power is still that number. Check. And then lastly, 1/4 is the base. -1 is the exponent. That's a -1. Let's erase that. Right, -1 equals 4. So that works because if we raise 1/4 to a negative exponent, we know that we can flip the numerator and denominator to get 4. So that's how you rewrite logs into exponential form. And now we're going to rewrite exponential form into logs on the next page. All right. So again, keep in mind every one at the bottom here, A, B, C, and D, is written like this, and we have to rewrite it like that. Okay. So log of, what's the base? Base is 5. Maybe got to make that a little bit smaller there. What's y? 25 equals 2. There it is. Log base 25 of 5 equals 2. On the next one, same deal. Log base 10 of 0.1 equals -1. Again, keep in mind, this number here is always the exponent in log, right? This x is the exponent, okay, of the exponential form, all right? Log base 8 of 4 equals 2 to the 3. Log base 6 of 1 over 216 equals -3. All right, so again, keep in mind, exponent here, all right? So in logs, the thing that it's equal to is the actual exponent, all right? So eventually we're going to be using these logs to actually calculate the exponent. Like here, it's relatively obvious, and we're given what the exponent is, but later on, not in this chapter, but later on, we're going to be going over how you can calculate a tricky exponent. For instance, like back on page 1, if you remember, that 2 to the x equals 6. There's actually a way to calculate that using logs. But again, we're not going to get into that yet. We're going to just get used to the whole format and how to put things from exponential to logarithmic, so on and so forth. All right. Okay. So let's actually calculate what these logs equal. Now, every single one of these, right, is written like that. And basically what we want to do is find x, which remember, x is the exponent. So basically we're looking for the exponent, all right? So you know what, let's make all of these look more like this right here, okay? And let's go ahead and give them letters. Why don't we say equals D equals, let's not use E, just put, whoops. So D, F, let's not use E because E can stand for, you know, the number E that we went over in the last chapter, okay? Call this one G, and running out of room here, equals H, okay? Now we're gonna rewrite it in this form, okay? So log base 4 of 64 is D. Now I want you to remember D, F, G, H, they all represent the exponent. So it's literally 4 to the D equals 64. So you know what, let's just set them all up first, all right? Log base 5 of 0.2 equals F. Now remember again, F is the exponent, so to the F equals 0.2. Log base 1/5 raised to the G, and that 1/5 should be in parentheses, equals 125. Log base 36 raised to the H equals 6. Okay. All of these are solvable without even needing to use a calculator. Like I said before, eventually we're going to get into ones where you can't solve it without a calculator, but these ones you actually can, all right? So we basically have to figure out, going back to example 1, okay, or example 3 part A, what D represent, or what D would be to make the answer equal 64. Well, 4 times 4 times 4, is 64, 4 to the third power. So D is 3. This one can be a little tricky. Now, 5 raised to a certain power gives us 0.2, so it became smaller. So raising it to an exponent, okay, that is a number like squared or to the third or to the fourth, that's just going to make it bigger and bigger and bigger. We want to make it smaller, all right? Using a fraction in this case is going to work out. The number you actually want to use is -1. Because if you think about it, 5 to the -1 is 1 over 5. What's 1 over 5? 0.2. All right, and I'll make it clear that the ones that you actually have to evaluate, I mean, I'm only going to give you ones for now in which you could do this in your head. You basically just need to be able to set it up and then go from there. G, we know that 5 to the third is 125. Well, how do I change 1/5 into 5? Negative exponent. G to the -3. It'll flip the 1/5, making it 5 because of the negative, and then 5 to the third is 125. And then finally, H, we know the square root of 36 is 6. Well, how do we represent the square root as an exponent? 1/2. And there it is. Okay. The next thing we have to go over is a common logarithm. A common logarithm is a logarithm with base 10, meaning that b is a 10, okay? It is denoted by log 10, just like I said a second ago, or simply by log. Now, basically what this means is, and it's actually already written down here, that these two things mean the same thing. So even if I don't put the 10 there, the 10 is going to be implied, all right? So keep that in mind. So basically, I'll show you what I mean by that. So if we add log 10, that's a 10, x equals f, and I wanted to rewrite that in exponential form, okay, it would be 10 to the f equals x. And we went over how to change from one to the other on the previous page, right? If I had just wrote log x equals f, okay, it's the same exact thing, okay? The 10 is implied. So this literally also means 10 to the f equals x. So notice these two things are exactly the same, all right? It's actually a lot like, let me just put this on the next page, separate from this. Think of it like this. When you write this, you know that that is a square root, even though there's no 2 there, right? Technically there is a 2, but without that 2, you still know that that's a square root. Any other root needs a number there, all right? That's kind of the idea behind base 10. If the log is base 10, you can actually just, it's used basically so often that it's just a little shortcut. So if it's not there, log base 10 is implied, okay? Moving on, a natural logarithm is a logarithm using base e, and it can be denoted by log e, but is usually denoted by ln, okay? So log base e of x equals, let's just call it g, okay? And once again, I'm basically going to rewrite this like that. Oops, sorry about that. So if I was to rewrite this in exponential form, it would be e to the g equals x, okay? Now, this is the same as that. So ln x equals g, okay? This whole thing and this whole thing will give you the same exact thing, okay? So notice, these two things are the same, all right? So things to keep in mind is that basically those two logs are used a lot. Okay, a log of base 10 and a log of base e. So these are just two other ways to denote those. Okay, so let's actually go ahead and calculate this on our calculator. Okay, starting with a. And I'm going to calculate log of 8. And you know what? Let's just write equals x. We'll just give it some variable. All right. Now, I want people to remember that technically what this means, since there is no base written down, what base is implied? Base 10, right? So literally, this is 10 to some exponent equals, equals 8. Let's erase that. Equals 8, okay? And the way you are going to do this in your calculator is by hitting the log button, hitting 8, closing the parenthesis, and then just hit equals. And you should end up with x equals, and I'll just write as many decimals that show up, 0.903089987. Okay. Now, this is the exponent right here. If you raise 10 to this number, you are going to get 8. That's what that x represents. Okay. All right, now let's do the next one, part B. So B is ln natural log 0.3 equals y. Okay. Now just remember, this is the same as log base e of 0.3. Okay, and this can be rewritten as, well, I'll just write it down. Log base e of 0.3 equals y. But again, you're going to see it written like this whenever base e is used. And this rewritten in exponential form is e to the y equals 0.3. All right. So basically what we're figuring out is what exponent y is going to give us 0.3 when we raise that exponent for e here. Okay. So literally in your calculator, we're typing in natural log 0.3. Okay. So you might actually already see that button on your calculator. It is right below the log button, right there, ln. So literally type in ln, and then type in 0.3, close the parenthesis, and you should end up y equals, it's going to be a long decimal once again, negative 1.20397, blah, 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 goes on forever. Okay. If you take e and raise it to that number, you are going to get 0.3. So again, this is a way to calculate complex exponents with certain bases. For right now, all we've been able to do is just calculate it with base 10 and with base e, with common logs and natural logs. Eventually, once again, we'll get into more complicated ones, but for now, we'll just stick to these. Okay. Inverse properties. So, by definition of a logarithm, it follows that the logarithmic function g of x equals log b of x is the inverse of the exponential function f of x equals b to the x. Okay. That's a great sentence, but it doesn't really explain how one is the inverse of another. Now, we remember inverses as being able to switch the x and the y, right? So let's show that when we switch the x and the y, we can end up back at the inverse that it's saying it's at, okay? So let's start with this guy. And remember, the g of x is just taking the place of y, okay? So y equals log b of x. Now, remember, an inverse is just switching x and y, right? That's all it is. So let's take the inverse. X equals log b y. Okay? That's the inverse, right? Inverse. When you're trying to actually calculate the inverse, though, you want to get y now by itself. Now remember, we can rewrite this in exponential form as b to the x equals y. And look, y equals b to the x, y equals log base b of x, which are the two inverses that they spoke of. Okay. We can do it the other way as well. All right, let me, we can just erase this and start with y equals b to the x. And again, remember, inverse is just switching the x and the y. We can rewrite this as a log, okay? So this is going to be log base b of x equals y. And once again, notice, and again, remember this is an inverse of what I had written right here, okay? Those two things that I just highlighted, this guy and this guy, inverses of one another. And if we remember back from when we did talk about inverses, if we actually plug one inverse into another, we should end up with just x. Same thing right here. That's what this whole situation here is explaining. Let's actually do an example that shows that this indeed does give us x, and this indeed does also just gives us that particular number. Okay. So I just rewrote what was on the previous page right here, and basically in order to make this equal just x, the two numbers here have to be the same, and then the exponent of this particular base has to be the same as this number right here. Okay, so let's look at an example. Let's let b equal 2 and x equal 3. Okay. So we all know that 2 to the 3 is 8. All right, that's true. I can rewrite that as log base 2 of 8 equals 3, right? We know that to be true. Again, all I'm doing is just rewriting this guy as this guy, okay? I am going to substitute this 8 with 2 to the third power. Why can I do that? Well, 2 to the third power equals 8, right? Doesn't it? It does. So it's going to look a little weird, but log base 2 of 2 to the third power equals 3. Again, all I did was substitute this. Now look at this. 2. The base there is the same. Here, those two numbers are the same. Okay. Now, with those numbers, those are the same. So literally, if you can make these two numbers be the same, then whatever this is, that is what the answer has to be. And we just did this by using numbers that we already all knew. Okay. And the reverse works as well over here. Okay, so let me show you. and we're just going to use the same exact numbers again. Okay, so so what would be the best way to let's do log 2 of 8 equals 3. Okay, again, we know that to be true. Literally talks about it over here. 2 to the third power equals 8, right? Okay. I'm about to use substitution to make something like what's up there, okay? We know that log base 2 of 8 is 3, right? So that means that wherever there is a 3, I could substitute in this guy right here. Well, here's a 3. So 2 to the log base 2 of 8, okay? And all I did was just substitute it, equals 8. Let's take a look. Base and the base are the same. If those are the same, this number yields this number. So basically, if you can make that happen, you can calculate the answer right away. Okay, so let's go on to the next page, and let's actually go ahead and calculate these values. And it may look complicated, but remember, we got these little helpful hints at the top. Okay, so start with A. Now, this guy looks a lot like that. It's got its base raised to a log, all right? And remember, when the log is isolated like it is, where there's no base written under that log, okay, what base is implied? So just to rewrite this bigger, 10 to the log of 4, okay? Remember, when it's just written log of 4, the base 10 is implied. So 10, 10. B and B are the same. So that means that if those are the same, then this literally has to equal that number, giving us 4. And that's it. Now let's do B. Okay. Now this guy is looking, whoops, undo. This guy is looking a lot, just trying to get that out of the way. It's looking a lot like that guy, all right? Right here. So we got log of 5, so that little b is the 5 here. But that number, sorry, keep hitting something by accident. But that number 25 is not the same, right? Because it should be the same. This should be a 5, okay? Well, what could you represent 25 as to make a 5 involved? 5 squared. So we could rewrite this as log of 5, log base 5 of 5 to the second, and then that is raised to the x power. Now, if you remember, when you raise a power to a power, what do you do with exponents? And by power to a power, just to be clear, I'm talking about that 2 and that x. Log base 5 of 5 to the 2x. So, just to be clear of what we have, these two numbers are the same. That's what we wanted right here. When that happens, simply gives us that answer, 2x. All right, so that is a way we can actually calculate these is by using their inverses. So no calculation needed, anything like that. Basically just kind of like manipulation in order to find out our answer and remembering rules. So next page, find the inverse of each function. Okay, so what we can do, let's write y equals 6 to the x. Switch the x and the y to get the inverse. Okay, remember that is the inverse, but I really want to get y by itself. Well, how do I rewrite this? Log base 6 of x equals y. There's our inverse. And we've already gone over how 6 to the x and log 6 of x are inverses of one another. We literally just went over that on the previous page. But this is it. Okay. Oh. Okay. So now over on this one. Y equals the natural log of x plus 3. So once again, let's just make it an inverse. Switch the x and the y. X equals natural log of y plus 3. Now remember, natural logs, right? They literally mean just logs of base e. So I could rewrite this as x equals log base e of y plus 3. And now I could rewrite this as e to the x equals y plus 3. Subtract 3 from both sides. So the inverse is y equals e to the x minus 3. All right? So it's basically about manipulation, going back, looking at the rules, getting used to those rules, because it can be a little bit overwhelming at first, all right? But just remember that you're going to want to keep going back, looking at the rules, looking at how to substitute it and whatnot. So keep that in mind. Okay. Graphing logarithmic functions. Sounds complicated, but it's going to incorporate a specific concept that you guys have actually seen before. All right. You can use the inverse relationship between exponential and logarithmic functions to graph logarithmic functions. Okay. The graph f of x log base b of x is shown below for b is greater than 1 and for 0 is less than b, which is less than 1. So just to be clear, it's referring to this guy right here. Because f of x equals log b of x and g of x equals b to the x are inverse functions, the graph f of x equals log base b of x is the reflection of the graph g of x equals b to the x in the line y equals x. Wow, lots of words. Remember though, you have gone over how inverses reflect over y equals x, right? So you actually already know how to graph an exponential function, okay, which is right here. We can graph that very easily. So if we can graph that one, we can then reflect it over the y equals x line and then graph our logarithmic function, which is exactly what we're going to do. And remember, when it comes to graphing lines and reflecting them, when it comes to inverses, you just switch the x and the y. So let's go over that. And by the way, it also works for logs like the one over here as well. Same idea, reflects over the y equals x line. Okay. So let's graph f of x equals log base 3 of x. Okay. We're not going to graph that first. What we're going to graph is the inverse. Okay. We are going to graph the inverse, which is g of x equals 3 to the x. Okay. Now, the way we're going to do this is by plug. And by the way, we know that this is the inverse. We went over what logarithmic inverses are. We've shown that multiple times. So we are literally going to replace x with these numbers listed in the graph below. So if I raise 3 to the negative 2, what am we going to get? 1 over 9 is correct. When I raise 3 to the negative 1, what am I going to get? I am going to get 1 over 3. When I raise 0 to the 1, or sorry, 1 to the 3 to the 0, what am I going to get? 1. When I raise 3 to the first, what am I going to get? 3. And when I raise 3 to the second power, what am I going to get? 9. Okay, so this is what the function will look like. Okay, and why don't I go ahead and graph that on the other page? Okay, so again, this is not going to be pretty. It's a little bit hard to draw on this thing, but I'm going to try my best. Let me start with the easy ones to graph. I got 0, 1, 1, 3, 2, 9. Oops. And then negative 1, 1/3, and then negative 2, 1/9. So it's going to look like this, getting closer and closer to 0. Huh, not bad. Okay, now remember, this needs to reflect over the y equals x line. So again, I'm going to try to draw, let's draw dotted line right along the y equals x, right? Okay, that's pretty close. Let me just extend this out a little more. Okay, cool. Now we can go ahead and try to reflect these points over, or we can remember that in an inverse, you just switch the x and the y. So why don't we literally just go ahead and make a function table again. And remember, this is going to be the values for the original function, f of x equals log base 3 of x. So f of x. And all you do is just switch the x and the y. So we're literally just switching these two. So now x is 1/9, f of x is negative 2, and then so on and so forth. So 1/3, 1, 3, 9, negative 1, 0, 1, and 2. So again, all I did was just switch these two, put them here, switch these two, put them here, switch those two, put them here, switch those two, put them there. Okay? So let's go ahead and graph these. I'll graph the easy ones again first. So I got 1, 0, right there, 3, 1, here, 9, 2, right there. And then the other ones, a third and negative 1, so like right there. And it's going to get really close to that y-axis, but not going to touch it. Right? And there it is. So if you can graph an exponential, which is relatively easy, when you graph a logarithmic function, all you got to do is just reflect it because they're inverses of one another. All right. I hope you found this video helpful. Please let me know if you guys have any questions.